So earlier we had covered Newton's third law, which is the idea that forces come in pairs, and that pair happens between two different objects, and each pair of those forces have to be the same in amount, in magnitude, and opposite direction. Now we're going to do Newton's second law. The way I write it out is a little bit different than the way your book writes it out, but it means the exact same thing. So pick whichever version you like better. Here's mine. The net force acting on an object will be equal to the mass of the object times its acceleration. Now, the net force is a vector in that it has to have a direction, and so is the acceleration. How about I point out that this would be the cause, right? You're going to apply a net force to an object, and then what happens is the object will accelerate, so that is the effect. Now that can get to be a little bit much to write every single time since we're going to use this a lot. So let's abbreviate it. So instead of saying the net force on an object, we'll just say F with a little net is equal to the mass of the object times the acceleration of the object. But what if we were just doing this in components? What if we didn't want to look at it as a full vector where things could be like 60 degrees above the horizontal? We could break this into components. So you could also do it this way, where F net just along the x direction would be equal to the mass times the acceleration along the x direction, and F net in the y would be equal to the mass times the acceleration in the y direction. So these are interchangeable, but when we're going to be doing math with it, we tend to use this way because it's a lot more accurate to find the components of the vectors and then actually just use a calculator to add the components than it is to actually sketch out all of the arrows with protractors and draw them tip to tail, tip to tail. So the mass here is a scalar, basically meaning it's a number that doesn't have a direction. And this is a vector. It is a number with a direction. So when you're multiplying like this, a scalar to a vector, what this mass is going to basically be able to do is take that arrow and make it longer or shorter, but it can't change the direction. So these two actually have to be the exact same direction. Otherwise, again, you've broken physics. So F net and A must be in the same direction. And if you take a second, let's think of the units here. The units here are newtons. Units of mass for SI is going to be kilograms. And the units of acceleration are meters per second squared. So we need a way to make all these units kind of work together that we don't have yet. And it's right here. It's just a conversion factor. 1 Newton of force is equal to 1 kilogram meter per second squared. And on one hand, you could memorize that, because you should know this for the class, or you can always just remember to come back and look at this equation to figure it out. 1 kilogram times 1 meter per second squared will give you 1 Newton. The units of force are equal to the units of mass times the units of acceleration. And it's a 1-to-1 conversion factor. All right, that's how 1 Newton was defined. So if you see a Newton, you could erase it and write in kilogram meter per second squared. If you see kilogram meter per second squared, you could erase it and just write Newton. I'm going to cover Newton's first law now that we've done Newton's second law. Because Newton's first law is built right into Newton's second law. So Newton's second law is the net or unbalanced forces on an object would be equal to the object's mass times the acceleration. Now Newton's first law says that if this is 0, there's no net force, then this is 0. There's no acceleration. That's it. That's Newton's first law. If there's no net force acting on an object, it can't have an acceleration, which means that its velocity is constant. And remember, velocity would be its speed and its direction. So if you wanted to do Newton's first law in words, it would basically be that an object will move at a constant speed in a constant direction until a net force acts on it.